And let's look at more applications of differentiation. In this particular section, we'll take a look at increasing, decreasing functions and the first derivative test. And they are related, right? Increasing, decreasing functions are related to the first derivative test. Okay. And we will learn how to determine the intervals on which a function is increasing or decreasing. We will learn how to apply the first derivative test to find relative extremes of a function. First one, let's take a look at increasing and decreasing functions. First one, let's take a look at the definition of increasing and decreasing functions. A function f is increasing on an interval if for any two numbers x1 and x2. So let's say, okay, we have x1 here, x2 right here. So f of x1, that's that. F of x1, this is x2, f of x2 is here. So if x1 is less than x2, because if x1 is on the left hand side of x2, then if guarantee that f of x1 less than f of x2, meaning y value at x equals to x1 is smaller than the y value at x equals to x2. That means it's increasing interval. Okay, a function f is decreasing on an interval if for any two numbers x1 and x2 in an interval, and if x1 is less than x2, it's guaranteed that f of x1 is always greater than f of x2. F of x1 is always on top of f of x2, then this will give us a decreasing interval. Okay, that's a difference between the increasing and decreasing interval. They are exactly opposite. The function is increasing if as x moves to the right, its graph moves up, just like this. As you go to the right, it moves up, then it's increasing. And then as x moves to the right, the graph moves down like that. Then we know it's a decreasing interval. You move from left to right, it's flat, just like that. That means it's a constant interval. Okay. And then if you look at it, for decreasing interval, the slope of tangent line at every single point is gonna be negative. You look at all these lines with a negative slope. And for the constant interval, every single slope equals 0, meaning it's flat. So slope equals 0. And then all the increasing intervals, the slope of tangent line is positive. So this is all negative. 0 here and positive here. So in this particular example, from negative infinity to a, it's a decreasing interval. And from a to b, it's a constant interval. And from b to positive infinity, that's increasing interval. Okay. So the test for increasing and decreasing functions, that have to be a function that is continuous on a closed interval a comma b, at the inverse interval on an open interval a comma b. If f prime of x, which is slope of tangent line, is greater than 0 for all x in open interval a comma b, then f is increasing on a closed interval a comma b. If the slope of tangent line is less than 0 for all x in a comma b, then f is decreasing on a closed interval a comma b. If slope of tangent line equals 0 for all x in a comma b, then the function f is constant on a closed interval a comma b. Let's take a look at first example, intervals on which f is increasing or decreasing. Find the open intervals on which f of x equals x cubed minus 3 over 2x squared is increasing or decreasing. So we're going to apply the test really quick, but before that we got to find the derivative of f of x, f prime of x. So apply the power rule, we get a 3x 3 minus 1 minus 3 over 2 times 2 times x 2 minus 1. So we get 3x squared minus 3x. We look at this factor of 3x, then we get x minus 1. Then use the zero factor property, setting 3x equals 0, setting x minus 1 equals 0. Then solve for x. Divide 3 from both sides of the equation, adding 1 from both sides of the equation. Cancel 3, we end up with x equals to 0. Here x equals to 1. So basically we have two critical numbers. And now if you look at it, it's two critical numbers, we separate the domain. Domain for any polynomial function is from negative infinity to positive infinity. So these two numbers, 0, 1, we separate the domain into three different intervals, three sub-intervals. Okay, first of all, put down test interval. The first one is from negative infinity to 0. Second one from 0 to 1. Third one is from 1 to positive infinity. I'm going to pick a value from each interval. X equals negative 1, x equals half, x equals 2. Okay, then, and let's find the sign of f prime of x. So let's find f prime of negative 1 first. So it's 3 times negative 1 squared minus 3 times negative 1 becomes 3 plus 3, which is 6. 6 is definitely positive. That means, so this interval is increasing interval. The second one, place x with half in the first derivative. So we get a 3 half square minus 3 times half, which end up with negative 0.75. So this is definitely negative. Negative indicate decreasing interval. And the third one, 3 times 2 squared minus 3 times 2, which is 12 minus 6, which is also 6. 6 again is positive. That gives us an increasing interval. So as you can see, the increasing intervals from negative infinity to 0 union 1 to positive infinity, and decreasing intervals from 0 to 1. Okay. So this is just a solution what we just cover, and the table below. This table is super useful, and you definitely should utilize the table to to test the interval for the increasing and decreasing intervals. Okay, and then the two critical numbers in this case is super important to separate the domain into 3 different subintervals and test each interval correspondingly. If you look at a graph, right? Our graph look like this. From negative infinity to 0, it's going up. The graph is going up. So it's the slope tangent line here is positive, right? And from 0 to 1, it's decreasing. The slope here is the slope tangent line here is negative. From 1 to positive infinity, okay, it's going up. Then the slope tangent line is positive again. Okay. So let's take a look at the procedures for finding the intervals of which a function is increasing or decreasing. For assuming f be continuous on an interval, on an open interval a comma b, to find the open interval on which f is increasing or decreasing, use the following steps. First step, locate the critical numbers by finding the derivative, right? Set equals 0. Find the critical numbers and use these numbers to determine test intervals. And second step, determine the sign of f prime of x and 1 test values in each of the intervals. Third one, use the theorem to determine whether f is increasing or decreasing on each intervals. Okay. And these guidelines are also valid if the interval a comma b is replaced by any of the following 3 intervals involving the infinities, right? So a function is strictly monotonic if the function is increasing on an entire domain or decreasing on an entire domain. So let's look at this one, right? This one is totally increasing from left to right. It's going all the way up, right? So it's increasing all the way. So that means it's strictly monotonic. Could be all the way going down, right? Like this one. Okay. As you can see from left to right, it's going all the way down. It's already decreasing, so this is also strictly monotonic. The function shown below is not strictly monotonic because if you look at this piecewise function at 3 different pieces, the middle piece equals 0, which is constant function between 0 to 1. So that's between 0 to 1, this particular parts of the graph is actually constant. Although the other 2 pieces of the graph are increasing all the way, but the middle section is constant, that means it's not strictly monotonic. It's partially monotonic. And next thing is the first derivative test. So we're going to use the first derivative test to locate the extremas, if any. So the interval on which a function is increasing or decreasing is not difficult to locate the relative extrema of the function. So if the function goes from increasing to decreasing, so from increasing to decreasing, we have a indicate a relative maximum. If the function go from decreasing to increasing, indicates a relative minima. It's increasing, decreasing, relative mean. For example, like this particular example, f of x equals to x cubed minus 3 over 2x squared. From negative infinity to 0, as you can see, it's increasing, right? From 0 to 1 is decreasing. At this point, 0, 0 is relative minimum. And here is decreasing until increasing. So at this point, 1 and negative half. That's a relative minimum here. Okay. So you can easily use this neat rule to determine the relative extremas. Okay, so let's take a look at the first derivative test. Let C be a critical number of a function that is continuous on an open interval I containing C. If f is differentiable on the interval, except possibly at C, f of C could be classified as follows. If f prime of C, meaning slope of tangent line, changes from negative to positive, this is negative to positive, then we have a relative minimum here at x equals C. So if you put it as increasing, decreasing interval, then we have decreasing to increasing. Then we have relative minimum. Here, second scenario, if the slope of tangent line changes from positive to negative, positive meaning increasing, to negative, which is decreasing, then relative maximum occurs at x equals C. If the side does not change, meaning if it is increasing, still remain increasing, right, then there's no extrema. If it's decreasing, still remain decreasing, or the slope of tangent line stays positive all the way or stays negative all the way, then there's no extrema. Okay, that's the essence of the first derivative test. Okay, so let's take a look at this example and apply the first derivative test. Find the relative extrema of the function f of x equals half of x minus sine x in the interval 0 to pi. So it's a predetermined interval 0 to pi. So in order to find the relative extremas, first step, we gotta figure out increasing, decreasing intervals. In order to do that, we need to find the derivative of the original function. So using the power rule here, half of x becomes half times 1, and derivative of sine x becomes cosine x. So the derivative becomes half minus cosine x. Now we're going to set derivative equals 0, which means half minus cosine x equals 0. So that tells us cosine x equals half. And in between 0 to 2 pi, the x value is either equal to pi over 3 or 5 pi over 3. So basically we get two critical numbers in this particular predetermined domain. Now next step, we just got to do create a table, right? And perform a test. So now test intervals. The domain starts with 0 to pi over 3. Second interval is from pi over 3 to 5 pi over 3. Third interval is from 5 pi over 3 to 2 pi. So here we're going to pick test value for each interval. First interval we can pick x equals to pi over 6. Second interval we can pick pi over 2. Third interval we can pick pi over 6. Now I'm going to replace all these into the derivative sine of f prime of x. So we're going to replace f prime of pi over 6. So you get a half minus cosine pi over 6. Cosine pi over 6 is radical 3 over 2. Now make this negative, less than 0, so we have negative. That means it's a decreasing interval. And second test value f prime of pi over 2. So end up with half minus cosine pi over 2. Cosine pi over 2 is 0, so it's half minus 0, which is half. And this is positive. So this interval is increasing interval. The last interval test value is 11 pi over 6. So the half minus cosine 11 pi. And cosine in the third interval, in the fourth quadrant is positive. So it's going to be half minus radical 3 over 2. Which is also negative, so this is decreasing interval. Now if you look at it from decreasing to increasing, we have a relative minima. Occurs at x equals pi over 3, and relative maximum occurs at x equals to 5 pi over 3. Okay, because from it's increasing to decreasing, then we have relative. Increasing to decreasing, then we have relative max. Okay, so that's basically pretty much it, right? So we locate both extremers. So as you can see, the table below gives us a very good idea. Basically, the increasing interval, decreasing interval. Utilizing that, applying the first derivative test. So at a pi over 3. So we go from decreasing to increasing. Relative minimum occurs at a pi over 3, right? And from increasing to decreasing, right here. Now we have relative maximum occurs at x equals 5 pi over 3. So actually graph confirms what we discovered.